Hello, and welcome to the third annual Python Web Conference. I'm Kim Nguyen from 6 Feet Up, and I am super excited to welcome Aditya Lohia, who will be speaking today on deploying machine learning solutions with low latency in Python. Over to you.
Thank you, Kim. Thank you for the introduction. So I would like to thank 6 Feet Up for in calling me up on the stage for giving this presentation. I am very passionate about deploying ML solutions. I am a machine learning engineer in Guys AI. It's a computer vision company based out of US. So my main task is to train machine learning solutions as well as deploy it on different edge devices, which includes Jetson Nanos, Raspberry Pis, etc. I have, yeah. So I think we can start with the presentation. So yeah, as I introduce myself, and you can find me on LinkedIn and my website. So yeah, so I've been looking at the research going on in the field of object detection, computer vision, and I see that researchers have been deploying some amazing algorithms with which push the accuracies over and over again every year, even in fact every month. And one problem that I notice every time is how do you deploy those algorithms? So even when I try to implement an algorithm and train it using our own custom data sets, the main problem is actually deployment. You can either deploy it on the cloud, but when it actually comes to deploy on the edge, it is a very big problem as the models can get quite big and can consume a heavy load on the devices. And there are many issues like the devices can heat up, you can observe a power load, etc. And you often notice that if you deploy a algorithm like ResNet 101 on the Raspberry Pi, if you are able to deploy it, you will often observe that the latencies are quite high and the throughputs are quite low. And what do I mean by latency? So latency is a term defined as the time taken by a machine learning algorithm to process an image, and throughput is the total time taken by the machine learning algorithm to process multiple images. So we often want low latency, whereas we want high throughput. And as so, this is the general structure of how you develop a pipeline for your project. So it goes from input data to the output, wherein you have multiple steps involved. So each step can be a bottleneck, but for this presentation, I would like to first focus on the model inference part and then move on to the entire pipeline. And when I talk about model inference, I talk about when you are trying to deploy algorithms as big as YOLO v4, YOLO v5, ResNet 101, ResNet 151 on the cloud as well as on the edge, as I've mentioned before. So this is generally the bottleneck that we have. And there are several methods by which you can improve latency and improve the throughput side by side. So there are four methods that I love, and one is weight quantization. So suppose you are using TensorFlow or you're using PyTorch for your framework to train and then use the algorithms. You often do that in float 32. That is the default format that you get. However, you can actually scale it down to float 16. That is, you reduce the memory by half, and that certainly will improve your latency as well as throughput, and also improve the GPU memory and decrease the GPU memory that is consumed, while also improving the power load. And you can further move on to actually scale it down to int 8. That is a format that is quite new for me as well. So for doing that, you often observe that when you scale it down to int 8, you see that there is a drop in accuracy, whereas for float 16, there isn't. So for the drop in, to take care of the drop in accuracy, there are two methods that we can utilize. So one would be post-training quantization, wherein you have a data set specific to quantization. That is that you will use that data set to calibrate your weights of the model. And that would be done after training during the deployment phase. And then another method is actually quantization over training. So in that, what you can do is you can set up a pipeline of training where you are making or forcing the models to learn or to transmit the weights and int 8. That is, you also project your gradients in int 8, and that is certainly a better improvement over post training quantization, because that is often the method by which you can get the most accuracy out of int 8 calibration. Moving on to the next method, that is model pruning, and this has been quite famous over the past couple of years. Uh, Due to that, you can specifically remove certain layers and certain connections between different layers of the network, and you might also notice that there is absolutely no drop in accuracy, and you can often observe a better speed because of it, and you are basically reducing the weights calculated by the algorithm and by the machine, so that is certainly helpful. The next method is knowledge distillation. So this is coming up right now, and the basic idea is that you take a bigger model which is trained on a quite heavy data set, and or definitely with a bigger model you get complex features, and with complex features you might get better accuracies. Suppose I would like to give an example of ResNet 151, and you train that ResNet 151 on ImageNet dataset. Now, simultaneously, you train a ResNet 18 on the ImageNet dataset. You might see that there is a huge difference in accuracy. There is a huge gap between those two accuracies. And I am certainly assuming that you have selected all the right hyperparameters for both the training methods. So nothing else is amiss. Only that the ResNet 18 network, because of less number of layers, is able to learn quite less, and the features are quite on the low level, whereas for ResNet 151 they are quite high. And so using knowledge distillation, what you can do is you can basically make the ResNet 18 model learn the knowledge that is gained by ResNet 151 by training on that huge data set, and for how many hours you might train it to. Yeah, so basically you'll get the same accuracy. I would not say same. Yeah, similar is a better word. You'll get a similar accuracy as ResNet 151 with the improved latency and improved throughput given by your ResNet 18 model. And yeah, simultaneously also decrease the power load and GPU memory. And the last method is framework based deployment, and that is the focus of my talk today. So there's a framework by the name of TensorRT. It is developed by NVIDIA, and I haven't seen this framework used by many companies nowadays. There is a lack of advertisement, definitely. So what is TensorRT? So TensorRT is actually an SDK for high performance deep learning inference, and it includes scratch built deep learning inference optimizer and a runtime, and it can take care of your needs for deploying low latency algorithms, and it has support for both Python and C++. So even if you are a C++ developer you can do it, but I love Python. I've been involved with Python for over 5 years now, and yeah, so I generally prefer to use Python even in my machine learning pipelines. And so it does not have a shortage of frameworks to convert from. So you can train your algorithms in any framework that you want: TensorFlow, PyTorch, MXNet, Theano. And you can simply use TensorRT's development API to convert it to TensorRT weights and then use it to deploy. I have attached some links further down in the pipeline. I'll share the presentation with you. So one might wonder, how does TensorRT do this? How is it able to outperform every known deep learning framework in human existence? So typically, if you take a trained neural network, TensorRT applies certain functions and certain optimizations to it, and it generates an engine that is specific to a machine. So if you are generating an engine on suppose RTX 2080 Ti, you cannot use that engine on any other GPU. You will have to go with RTX 2080 Ti's only. So it is specific to machine, and that is because of the certain optimizations that it does. So yeah, so that is one thing that we'll focus on about TensorRT. So the first is that it does weight and activation precision calibration. So as I talked about the weight quantization, it is similar to that. Actually, it is same. And TensorRT basically what it does, it quantizes the full precision information to int 8 while minimizing accuracy loss. And to do that, TensorRT performs a process called as calibration. in which you'll have to supply a data set to it, and it will change and it will reconvert the weights and its activations to 8-bit integers using that data set. And so no additional fine tuning or retraining of the model is required for this step. So you do not even have to do the quantization aware training to do this, and you can still get similar accuracies to quantization aware training. And yeah, also the calibration is completely automated, and it is a parameter free method. So you do not have to worry about changing certain hyperparameters to actually achieve this goal. So the next, I'll talk about layer and tensor fusion from the next slide because it is quite a big topic. So moving on to kernel auto tuning. So as I talked about, so if you generate engine on RTX 2080 Ti, you'll have to use that on RTX 2080 Ti's only. You cannot switch GPUs. You cannot run that engine on any other GPU. So it is because TensorRT does kernel auto tuning. So basically what it does is, so it has already got specialized kernels for different GPUs. So when NVIDIA wrote this library, they actually wrote uh, kernels for different GPUs. It has yeah, I forgot to mention that TensorRT is only supported for NVIDIA GPUs right now. Yeah, and yeah, so the kernels that NVIDIA wrote are hand-tuned and they're optimized for a range of parameters and, as mentioned, for a range of target platforms. So, as an example, there are several different algorithms to do convolutions, and there are several different ways by which you can implement those. So, what TensorRT will do is TensorRT will pick the implementation from the library of kernels that delivers the best performance for that GPU. So the convolution layer that we talked about, the implementation or the kernel for that might work. One kernel might work better for RTX 2080 Ti, whereas the other will work better for RTX 3080s. So TensorRT automatically chooses it, and you do not have to worry about anything. So because of its automated kernel choosing for the specific GPU, you can get the best performance for the target GPU. You can reduce your latency, you can increase your throughput, and uh, basically you get the best parameters as well. So yeah, that is what kernel auto tuning is. Moving on, TensorRT also allocates dynamic tensor memory, so it reduces the memory footprint. So suppose I have used TensorRT quite some time now, and I've used it for many models or for almost every model that I deploy. So TensorRT, you suppose are using resonant. Suppose you are using ULO v3 to develop your pipeline, develop your object detection pipeline. So if you notice, it will consume about 4 GB to 5 GB of GPU RAM, GPU memory. Whereas if you deploy that same algorithm in TensorRT, it will use less than 1.5 gigs. So that is definitely a quite improvement, and you can run multiple algorithms on the same GPU because you have reduced the memory. And TensorRT does this. It improves the memory usage by designating memory for each tensor during the usage and not beforehand. So when that tensor is being used or when that tensor is being converted, it allocates memory only that. And the memory allocation is actually quite fast because they use the CUDA library and they do not do it using some conversions from CPU to GPU. So it has a very fast and efficient execution. Moving on, it also has support for multi-stream execution. So it has a scalable design so that you can actually run multiple streams together, that you can do it on the frameworks. So moving on. So what I love about TensorRT is this part, which is layer and tensor fusion, and that this is what has impressed me the most. So what TensorRT does is, so it reads your computational graph. So in this example, I have GoogleNet here with me. That was the winner of ImageNet competition in 2014. So TensorRT does several graph optimizations. So these graph optimizations do not change the underlying computation in the graph. So if you notice the left-hand graph and the right-hand graph, so the computations or the network isn't changed. So they basically go through the same computations, and your output does not change. So what that does is they only restructure the graph to perform operations much faster and much frequently. Sorry, more efficiently. So a particular deep learning framework for each layer and for each function, it has to do multiple function calls to the CPU as well as the GPU, and it happens for each layers. And for each layer on the GPU has to call multiple CUDA kernels, and it has to launch those CUDA kernels. Now the kernel computation is actually very less and very fast compared to the call, the function calls and the CUDA kernel calls, and also the reading and writing of the tensor data for each layer. So this results in a memory bandwidth bottleneck and underutilization of the available GPU resources. And TensorRT addresses this by vertically uh, fusing kernels to perform the sequential operations together. So if you look in the video, so it has actually fused the convolution layer, the bias layer, and the ReLU layer into one single layer. So when you call or when you pass the image to that layer, you do not have to perform three simultaneous, like you do not have to call functions for three layers separately. TensorRT does it all in a single layer. And this layer is typically called as a CBR. And the simple analogy is that instead of making three separate trips to the supermarket to buy three different uh, items, you just make single trip to the supermarket and buy all those three together. And TensorRT does the same thing here. And TensorRT also recognizes layers that share the same input data and filter size. So yeah, so if you look at on the left image, there are two layers, horizontal two layers, one by one convolution and one by one convolution. And TensorRT does horizontal fusing for these two, and it it is a single layer, and you do not like it is a single kernel, so you do not have to call uh, multiple times, but you have the same weights, and this does not change your output at all. You will get almost same accuracy. And TensorRT also eliminates the need for concatenation layers by pre-allocating output buffers and writing them into in a slided fashion. So you absolutely eliminate concat layers. This is what TensorRT does after fusing of layers. So if you look at the number of layers of VGG19, it has reduced it from 43 to 27. If you look at the layers of Inception V3, it has a drastic improvement. It's 309, whereas with TensorRT, you will only have to do calculations for the 113 layers. And similarly, if you look at Resident 152, it goes from 670 to 159. Now, just imagine the computation power that you will save, or the call multiple functions call that you are saving for each layer that is fused with another. And the TensorRT is quite simple to actually convert to. Your pipeline is quite simple to convert to TensorRT if you get the right way, which is mentioned in the developer guide of NVIDIA. So for Python, there are two ways. There are three ways that you can use with Python. So one is you can choose the step of converting layers from TensorFlow First, you will have to check if your model or if your original model is in TensorFlow PyTorch or MXNet. So if it's in TensorFlow, you can use the UFF parser, or else you can directly use ONNX. And for PyTorch and MXNet, you only have the option of ONNX parser. So you can convert the PyTorch model to ONNX, and then you can convert the ONNX model to TensorRT. And these conversions do not reduce the accuracy of the model. I have tested it with multiple models. And so another way is by using the network definition API of Python. So you can actually rewrite the entire network in TensorRT's API. You can load the weights to each layers and then convert and generate an engine. And the third method is by using C++. So you can write the layers in C++, and then you can use the C++ generated engine directly in Python. You do not have to do anything else. And then once you have an engine generated, you can directly use TensorRT's runtime to perform inference on the GPU. So if you look at, I'll have two metrics displayed here. This one is for retina phase. So it is one of the state of the art algorithms for phase detection. And I did my tests on GTX 180 using one batch size. So if you increase batch size, your performance is definitely going to improve. So I have the first two rows are for ResNet 50 based backend, and the third row is based for MobileNet backend. So I ran it using PyTorch and TensorFlow on GTX 1080, and I got a FPS of 30 for Resonate 50 for FP32, and for TensorRT I got a FPS of 81, and that is like double the improvement. And for Int 8 I got an FPS of around what 80, 81 for PyTorch, and for TensorRT I got 190. And just look at the FPS that you get using TensorRT or with a mobile net backend. It's 400, so you can run multiple streams over this. You do not have to worry about anything. The next one is YOLO V5. It is also one of the state-of-the-art algorithms for object detection. And I did my tests with on multiple batch sizes of YOLO small, and I did single batch size for YOLO medium and YOLO large. And typically with a YOLO small V5 small model on GTX 1080, you get a FPS of around 20 to 30, depending on how much memory or how much what is the image size for that network. If it's 608 by 608, you will get around 25. And with TensorRT, you get a FPS of 142. That is like quite a lot, honestly speaking. If you increase the batch sizes, you can see the increase in FPS over here. And for YOLO V5M and L, you get 65 and 67 and 30. And so these uh, layers like the small, medium, and large are typically the number of layers that each model will have. So small has the least number of layers, whereas large is the highest number of layers. So what are the best practices for TensorRT? So always use max precision for deploying uh, pipelines, because there might be some layers that won't be converted to int 8. You can use FP32 or FP16 for those. And you do not have to rebuild the engine for each inference. So if you are developing a pipeline in TensorRT, just reuse the already built engine on your development workspace instead of rebuilding the engine every time you run an image. And so workspace size is a concept in TensorRT. So it is the size of the entire workspace that your pipeline will be consuming. So it also includes the tensors for the network as well as the image size, images and everything. So you can set it, you can increase the workspace size for better memory, for more memory consumption, which will prevent uh, crashes of the pipeline. Things to keep in mind is, as I mentioned, engines are generated as that are specific to the machine. Also, installation without Docker actually takes quite a bit of efforts and time for TensorRT. And as I mentioned, there are multiple APIs for conversion. So moving on, so I wanted to talk about Deepsteam. It is quite a big topic, and I won't be able to cover much about it here. Yeah, so as I talked about the bottleneck that is model inference, Deepsteam is another SDK developed by NVIDIA, which takes care of the entire pipeline. It is a multi-platform scalable framework with TLS security. You can use Deepstream both on edge and on any cloud. It supports as TensorRT, Python, and C++. And one speciality about Deepstream is that they have used GStreamer objects, and they have custom developed it to run on GPUs instead of CPUs. So you can basically speed up the entire pipeline, and you can move that entire pipeline to a GPU. And it supports development using multiple frameworks. So even if you want to deploy anything using TensorFlow, PyTorch, or MXNext along with TensorRT, you can use Deepstream for that. So yeah, Deepstream takes care of the entire pipeline in one go. You do not, and model inference for Deepstream is taken care by TensorRT. So this is how a typical Deepstream architecture looks like. So on the bottom, you will have an NVIDIA compute platform. You can use containers, Jetson, T4s, and K8 GPUs. Then you will have your CUDA libraries. So there is the TensorRT CUDA, the Titan inference server, which is again another inference server that is used for deploying TensorFlow and PyTorch based models within Deepstream. And then you have the Deepstream SDK, which has several features in it. So it has hardware accelerated plugins that is using the GStreamer. They have done this, and they have converted and they've shifted the entire thing to uh, GPU. You have bidirectional IoT messaging, so you can actually pass on messages from one pipeline to another, and you can update the models without stopping the pipeline. So even if a pipeline is running, you can provide it OTA based updates like you often get in your phone. It also contains several reference applications for you to develop from, and it gives you several Helm charts to review. The application services can be used in both Python and C++. So this is how the Deepseam pipeline will look like. This icon is for multiple streams, and you can deploy ResNet 50 on Jetson Nano for 8 simultaneous streams using Deepstream. Each stream would give you an FPS of 30. So it's basically real time on the Jetson Nano ResNet 50 classification model. So these are several of the steps that are done on this. We specify GPU, CPU, and what plugins they might use in the backend. So for capturing the stream, they capture RTSP as well as raw streams, and they do this using GPUs. Now the streams need to be decoded, and these decode. There is a plugin NVTech. It is also based on the GPU. Tensor Deepstream uses it to convert it, so decode the layers. Then several image processing techniques like such as scale, dewarp, crop, those are done on GPU instead of CPU. And that is definitely a major improvement over CPU based preprocessing techniques. And after that, Deepstream automatically generates batches out of the given stream, so you do not have to enable that in your code. And this stream management is done on CPU and not on GPU. And then here DNNs are actually your algorithms that you are deploying on Deepstream, and this will be in TensorRT. Then you can Deepstream also gives you an package or inbuilt plugin for tracking, and that is deployed on GPU. It is quite good, in fact. And then you can then you can actually visualize your streams on the screen, and this encoding and decoding is done using GPU as well. And then you can push it to the storage cloud or display unit, and it supports various formats like HDMI, SATA, and NV. And this is the plugin that they use for doing that. So yeah, so these are several of the models that NVIDIA developed along with Deepstream. So as the name suggests, this is for detection of people. Traffic CamNet is for traffic detection. Dash CamNet is for detecting vehicles, people, the environment, based on a dash cam. And then you have a face detection algorithm. All of these are based on ResNet 18 or ResNet 34s. So you can see that Jetson Nano with a GPU FPS. This is quite a high inference resolution, and the model accuracies I mentioned, and the FPS is also mentioned. And moving on the right, you can see how it performs on different Jetson machines. And then finally on T4, it gives an immense GPU of over 800, over 1000, over 2000. So just imagine how many streams you can run using T4s. So these are several of the resources for TensorRT and for Deepstream. I'll be sharing this slide deck with you guys after the presentation. I'll show you the how you can essentially convert your models to Deepstream. I've used, as I told, I used Retina Face. So I have this repo. I'll also share this with all the attendees. Yeah. So here, so this is the path. This is the part of the file where I convert my PyTorch-based engine to an NX. So this is the configuration files for Retina Face based on MobileNet and ResNet 50. And basically, what I have to do is I just have to load the Retina Face model like this, and then PyTorch gives you an option of directly converting to an NX using torch.1nx.export, and you'll have to check the offset version for TensorRT, because some of the TensorRT versions might not use the latest offset versions. And basically offset versions are the operator sets that ONNX has. So several new layers are coming up day by day, and latest offset versions give you the latest conversions for those in ONNX. So this is how simple it is to actually convert a PyTorch based model or a TensorFlow based model to ONNX. You just have to write a single line. So then moving forward, we'll convert the ONNX based engine to TensorRT. So yeah, so here what I'll do is I'll just go to the get engine part, and what this will do is, so there are several parts of how TensorRT works. So one is the builder. So builder is typically the workspace in which you will create a network, and builder.create network would actually create a network, and you'll have to assign that network this variable to the uh, your model will be assigned to this variable. And parser is basically different parsers that are supported. So one in NX, another is UFF parsers. So you can use these parsers to convert your UFF or ONX based engines to TensorRT. So these are general steps that are common for every conversion. And yeah, so here I read the ONNX model that I converted, and I check the shape of the ONNX model, and then so -1 and -1. So this is the width and height of the input width and input height of the input layer. So when you set it to -1, you are actually telling the network this that these are going to be dynamic and not static. You can set it to anything that you want that the network takes as an input, and that would be assigned as a static. Only -1 will give you a dynamic engine. Yeah, and this is the number of channels of each image and batch size. So so for dynamic generation, you'll have to create an optimization profile in TensorRT. So what an optimization profile is, so you'll have to set the minimum input shape that you'll get, the medium or middle shape that you might, average shape that you might expect, and the highest shape. So TensorRT, what it does is it creates optimization profiles from the minimum shape to the output shape. So this actually reduces the computation time during inference. It generates it, then it saves those profile into the config, and then when you build the engine, it applies that optimization profiles to your engine. So if you give an input size of less than this, it will throw an error. If you give an input size of more than that this, then you'll get an error. But if you are providing input size between the minimum and maximum, it will be quite easy and quite fast. So then you can, so this is how you can serialize the engine. You just have to write it into a path, into a file, and you can name the file anything that you want. So this is how simple it is to actually convert PyTorch based models and Python based models to TensorRT. Mm, and yeah, so moving on to the inference part, you can just import these three libraries for TensorRT. The rest are for my use cases, and I set the different hyperparameters for it. And as I have the mobile net version converted, I just have the configuration for mobile net based retina phase. So this class is for the post processing of retina phase outputs. And yeah, so here, so you load the engine like this. You just have to create a TRT runtime and then deserialize the CUDA engine that you generated. And then, so yeah, so here you pass the engine, and you will obviously have to create a context, that is the context in which you will run or you will pass on the input images. And you'll have to set the activation, you'll have to set the optimization profile for it. So as we only have a single batch, we can set it to 0. For multiple batches, you can set a different context and different optimization profile. And yeah, so here in the detect function, I pass all these things to the detect function. This statement at 229, it binds the shape of input image to the context, and then you allocate buffers for it. And this step is the dynamic memory allocation. So this step actually reduces your memory consumption for the GPU, as you are only doing it during inference time. Then you set the input image to the input source, that is the memory that you generated. You do inference, and then you basically format your output however you want. This is as simple as it goes with any other framework. Now I wanted to show you another repo that is created by Mr. Wang Xinyu, and he is someone who has extensively contributed to TensorRT based deployments. He does his work in both C++ and Python. So as you can see, there are multiple models here that he has converted, and these models are converted using the C++ network builder API. And then he has given a support of deploying the generated C++ engines in Python. So I would definitely like you all to check this out, as he writes everything from scratch. He builds the networks from scratch, and then all the CUDA layers, and this gives you the best accuracy as well as the best speed. So yeah, I think this is it from my end. Thank you guys for inviting me.